Well, good evening. My name is Mr. Ashby. I'm here to actually tell you a bit about the physics you're going to be hopefully doing in Year 12 and a tiny bit about what you might be doing in Year 13. Now, at the moment, you are, I guess, you're halfway through bridging or you've done your bridging course and you're getting an idea about physics in, at A level. Okay. Just this slide also appeared in the bridging material, but I'll run through it again. My name is Mr. Ashby and I'm effectively head of Key Stage 5 Physics. If you've got any questions at all about the course, then please don't hesitate to contact me. This slide is on the bridging material, so you'll be able to find my email address there. Please do. Now in Year 12, the other physics teacher is Mr. Mickleborough. You might have met him. He teaches mechanics and waves, while I teach the particle physics and the electricity units. In Year 13, we're joined by Mr. Phillips, who then teaches the simple harmonic motion, thermodynamics, and field theory. We'll come to that later on. Now, when AQA wrote the course, what they tried to do was get the biggest overlap as possible with GCSE. The idea is, yes, it is a step up from GCSE to A level, but it's the first step you take. You should be reasonably familiar with. If we have a look at the Year 12 units, then I'll explain exactly what I mean. Right, waves is a Year 11 GCSE topic, and that's certainly where you meet it to start with. And so when you get to the waves unit, you think, oh, okay, I recognise a bit about this, and okay, then we move on to the A level bit. Mechanics is actually, well, forces and motion. We did an awful lot of that probably in Year 10 and Year 11, equations of motion and that sort of thing. Electricity, now that's very much a Year 10 topic, but we progressed that as well in the Year 12 in A level. The one you won't have come across before is something called particle physics, and I'll explain a bit more about that as we go. Now, just for completeness, at the end of Year 12, we have a look at something called circular and simple harmonic motion. Now, that's actually a Year 13 part of the course, but we do it at the end of Year 12. We also have a look at capacitors in Year 12, but it's a Year 13 topic. When you get back to Year 13, we then hit the proper hardcore physics, right? Electric fields, magnetic fields, electromagnetic fields, gravitational fields. I think you can see the trend here. Thermodynamics and nuclear physics. Now the field theory that's the real hardcore. That's proper physics. That's the real meat of the subject. But we hang back. You only meet that in Year 13 when you're all good and ready for it. Now, one of the Year 12 topics, Mr. Mickleborough teaches this, is mechanics. And I thought what I'd do for the first two topics is just kind of a quick introduction of what it's all about. And here's a picture of a tree, and this is mechanics in the sky. And the idea is I just want you to try and guess what the tree is, or why is it significant. While you're thinking about that, I'll give you a clue. I'll continue to voice over. It's an apple tree. And at that moment, you probably think, maybe something to do with Isaac Newton. And you would be right. This is actually the famous Isaac Newton apple tree, where there's two versions of the story. The first version, which is rubbish, is Newton sat under a tree, an apple fell onto his head, and he came up with the idea of gravity. Now that's just utter nonsense. Isaac Newton was a genius, and that's not really genius. The genius part of the story, what he did was he saw an apple falling from the tree, and he equated the force of gravity that draws the apple down to the ground, and he said, look, this is the same force that keeps the Earth in orbit around the Sun. It's the same force that pulls the Moon around the Earth in orbit, and that really is clever. Okay, so the mechanics. The first bit is Newton's laws. There we go. We study Newton's laws in more detail. Equations of motion, which you would have come across. You came across one equation of motion in Year 11, sorry, which is v squared is u squared equals 2as. V squared plus u squared is 2as. It turns out there's four of them, and they're all really useful, and they're all used to predict the path of particles. The end of that is something called projectile motion, where you can actually predict the path of a particle as it's, say, launched out of a cannon. at various angles, and you can predict how far it goes and what its trajectory is. And I think it's absolutely fascinating and great fun. You can try an experiment to see if you're right and predict these particles. There's all we do stuff on moments, which that's very much year 11, wasn't it? Momentum as well, which is right at the end of the forces in the year 11 unit. So all this stuff is not unfamiliar. It's just we take your understanding in year 11 and then we build on it into A level. Now, particle physics. This is something you won't have done anything on at all before. Okay, and it's absolutely fascinating. We used to teach OCR A-level physics, then we moved to AQA, and suddenly here we go, this huge great unit, particle physics, which wasn't in the previous course. And at the start, I was a bit, I don't know about this, well, what are they trying to do? But actually, it's now my favourite part of year 12. It's absolutely fascinating. It's a sort of historical introduction, and it leads right up to cutting edge physics, where physics is now what's happening at CERN. What we're looking at is a bubble chamber picture, and as a particle travels through the sort of an alcohol atmosphere, what it does is it leaves behind it a trail of bubbles, and we can see how these particles move through the atmosphere. There's small squiggly ones, you see them going round and round and round. I'm hoping you can see where I'm pointing the cursor. And these things are actually electrons. Okay, they're small, they're not got much mass, and they're pulled round in a circle. There they go. The interesting thing is that if you look at this one, this particle here, there's one swirly bit going one way, but there's another one going another way. And actually what you're looking at is you're looking at the antimatter of equivalent of an electron, which is a positron. Okay, so these are, is good evidence for antimatter. More of the same, but look, these large tracks, they are looking very similar to electrons, don't they? But they're much, much wider. So you think, well, what difference would the particle be that actually formed these? Now, the difference is it's got more mass, it's less inclined to change its motion. And these are basically heavy electrons, or muons. Okay. There are other particles on here. There's particles almost describing straight lines. Here's one here. There's another one there. Now, if it's almost describing a straight line, it must have a significantly greater mass than an electron. Okay. Now, these particles, I think, from this picture, these look remarkably like mesons. Now, mesons are something you won't have heard of before. These are called V particles, and you can get pi mesons or K mesons, and well, more of that in year 12. So particle physics, we start off by having a look at the fundamental forces of nature, and there's only 4 of them, and we have a look at how strong they are and how they interact. We then follow on to antimatter. Now, where's the evidence for it? What do we use it for? Now, interestingly, antimatter to most people is the stuff of fiction, but we use antimatter at the Norfolk and Norwich Hospital as part of the PET scanning system. Well, you go on to the particle zoo. Now, the particle zoo is so named because in the early part of the 20th century, from a very basic understanding of, we think there's protons, neutrons and electrons, as scientists we discovered more and more and more particles, and we were running out of Greek letters for them. there were so many, somebody coined the phrase the particle zoo, which describes it very well. So we'll have a look at all the particles and actually how we can classify them. The photoelectric effect was a very much particle physics thing, and it baffled scientists, physicists for years, and it took Albert Einstein to actually work out what was going on. Now, what I'll get you to do is we'll have a look at the experiment, and I'll get you to think like Einstein and see if you can work out what's the thought process, what's the evidence, how did he come up with his conclusions. Lastly, wave-particle duality, which is a very strange thing. It's very hard to describe it. If you take something like an electron, most of you are happy that an electron is a particle and it chugs around an electrical circuit and it's behaving like a particle. But we can accelerate a stream of electrons at a cobalt target and you'll find they diffract. And actually diffraction is a wave property. And we've got an electron diffraction chamber to show you when we do that. And so depending on the experiment you do, a particle can either behave as a wave or a particle, and it's an extremely odd idea, but it seems to fit the evidence, and that's why we stay with it. Anyway, yeah, right, on to practicals. Yes, there are required practicals, just like GCSE. At A level, there's actually 12. We do 6 in year 12, we do 6 in year 13. I'll run you through the year 12 ones. The year 12 ones, we start off with electrical ones. There's a resistivity. We look at the internal resistance of a potato. Mr. Mugabe will calculate a value for G experimentally. Most of you realise it should be roughly 10 or 9.81, and we'll see how close you get. Have a look at the standing waves on an oscillating string. Now, this was actually a year 11 practical, but we look at it in a lot more detail. We do a lot more with it. The Young's modulus of steel. Why? Now, the Young modulus of a material it's just a measurement of a property of a material that is independent of volume or length or anything. So it's a really useful thing to work out. We'll hang bits of steel wire from the top of a ladder and dangle huge masses off them. We'll work out its value for the Young modulus. Lastly is diffraction gratings. Now, actually, this is my favourite practical in year 12, and it actually sits in the waves unit. If you look at the backgrounds, what we're looking at is we're looking at the diffraction pattern of red laser light and green laser light, and I've got 3 different coloured lasers which we can analyse. And somebody actually said that diffraction grating was the most significant piece of equipment in astronomy in the last 100 years. And what you can do with it, if you've got a light source, we can use laser light. You could have a look, you point a diffraction grating at a light source from space. What you can do is you can pass light through a diffraction grating, and you can accurately work out its wavelength from how it interacts and how it goes through these things. So we'll work out the wavelength of light through green laser light and red laser light and purple laser light as well. That's one of the year 12 experiments. Now, normally at the end of year 12, we all head off to Switzerland, or most of us head off to Switzerland. We actually go around CERN, and now CERN is where particle physics is really happening at the moment. It's cutting edge. It's an absolutely fascinating place. What we're looking at is part of the tunnel where the accelerated particles travel through. This beam tube in the middle is where the particles travel. And the experiment basically is to accelerate 2 beams of particles at almost light speeds in different directions. Each tube here actually contains 2 streams, one going one way, one going the other. And at certain points in their circuit, they smash them into each other. Now, the idea of that is if you've got particles almost at light speed, they've got a huge amount of energy, and if you smash them together, they fall apart. But because energy and mass are conserved, then you make new particles. And what one of the experiments in CERN tried to do was they tried to detect something called the Higgs boson through very high energy collisions. And the Higgs boson is, well, it's not the end, but it's certainly a key piece in something called the Standard Model of particle physics. Now, hopefully, without going into a massive amount of detail, you might have had a look at the Standard Model in your bridging material. Anyway, we'll probably go to Switzerland again at the end of year 12. We'll have to see how it goes. Finally, yes, here we go. Everybody, I think, has got a favourite scientist. I mean, you want to study physics. My favourite physicist is actually an American called Richard Feynman. He's not Albert Einstein. He's not Isaac Newton. He's an absolutely fascinating character. Now, he grew up, he used to mend radios for his neighbours. He got into electronics. He worked on the Manhattan Project, which was the atomic bomb. He came up with the idea of quantum electrodynamics, which is really, really quite hardcore top-end physics. But he wrote a book, called Surely You're Joking, Mr. Feynman, about his life and what he'd been up to. And quite a lot of his life he just spent it doing interesting things. He went to South America and learned to play the bongos. He had to go at safe cracking because it was a challenge. Fascinating character. If you find you've done enough bridging and maybe your brain needs a bit of a rest over the summer break, get a hold of Surely You're Joking, Mr. Feynman. It's a brilliant read. I don't think you'll learn that much new physics from it, but at the end of it, you probably want to become a physicist, and in a way that's the point, isn't it? So that's pretty much it. Now, I hope to see you all in year 12, and I hope you enjoy the rest of your summer. Thank you very much.